Everyone, for those that have joined in the past few minutes, we'll look to get started probably about 5 after, so in about 4 minutes or so. Thank you. Hi, Everton. We're about to get started, probably in about 2 more minutes or so. Okay, everyone, thank you so much for joining tonight's virtual edition of the AWS User Groups of Florida Meetup. Tonight, James Beswick, who's a developer advocate at AWS, is going to walk us through S3 EFS and local storage for serverless. Just as a few housekeeping items, as you joined, you've been placed on mute. There's a little unmute button to unmute yourself if you have anything to ask questions about, etc. At the end of this, we'll place the presentation and the video on our meetup page. And as always, we try to have these meetups once a month. Being virtual, we're able to extend our reach, not just across Florida, but the US and beyond. If anyone has any feedback around items they'd like to see presented, presentations they'd like to provide, or any of that, please feel free to join us either through our meetup pages or through our Slack channel. With that said, go ahead and hand it over to you, James. Thank you.
Great, thanks very much. I'll just get my screen share sorted out. Hopefully everybody can see that okay. So yeah, welcome to today's talk. I'm going to discuss a variety of different data storage options that are available in AWS Lambda. So my name is James Bezic. I'm a developer advocate here at AWS Serverless, and I've been a serverless geek for about 3 to 4 years now, and I've built some fairly large applications using only serverless technology. And prior to being a DA, I was a software developer for quite a long time and also a product manager for many years as well. And I've worked in a variety of different startups and large companies. So the most important thing on this slide is my email address and my Twitter handle. So if you have any questions about serverless in the future, feel free to reach out to me anytime and I'll do my very best to help. So I want to just cover a few different things today and talk about some of the different storage options available to you with AWS Lambda. I'm going to cover three broad areas today. One is Amazon S3. The second is Lambda's local storage options, some of which you might not be aware of. And then also the new EFS for Lambda option. After this deck, I will show you a quick demo of these features and also open the floor to Q&A. So if you have any questions at all, I'll be happy to answer those. Each section, I'm going to highlight the main features of the service and the characteristics when you use them with Lambda. I'll also show some code examples in the deck as well and show how you interact with that data storage option. So let's take a look. So when you look at Lambda, let's talk about some of the features first of the service. So first, it's an on-demand compute service, which means it only runs when it's needed. And you pay for the number of times that your code is run, along with the memory used and the duration of your code execution. Lambda is a high availability service, so it runs in multiple availability zones. Now, this all happens behind the scenes. So in the event of service disruption in a single availability zone, Lambda will use a different AZ in the same region, and this is all handled for you. Lambda manages scaling automatically, so when your workload experiences higher levels of traffic, the Lambda service will increase the number of concurrent instances of your function to keep pace with that traffic. It also scales down as needed, which is important, without any manual intervention. Lambda functions are triggered by events. The event could be an HTTP call, an object written to an S3 bucket, or just a scheduled CloudWatch event. And Lambda natively supports multiple runtimes, including Python, Node, Go, .NET, Java, and many more. You can also bring your own custom runtimes, so that'll allow you to run runtimes like PHP, Erlang, and even COBOL. So each function has one runtime, but in an entire application, you might have lots of different functions, so you could potentially have different runtimes across an entire workload. So the first question with all of this is, where does Lambda store data? Well, it all starts with your code deployment artifact. So when you upload this to Lambda, the service stores the code durably in S3. The artifact can be up to 50 megabytes zipped or 250 megabytes in total when unzipped. When your function is invoked, the Lambda service fetches this code from S3 and prepares the execution environment. The deployment package is then unzipped into this execution environment, and depending on how you configure your function, you then have between 128 megabytes and 3008 megabytes of memory available to you. Every function has a /temp storage space. This is always available, and this has a maximum storage size of 512 megabytes. The deployment package represents everything that can be contained within a single Lambda function. So that includes all of your code and dependencies and also any Lambda layers. Now, after your invocation finishes, the execution environment will be destroyed at some point soon after, deleting all of the memory and the temporary storage space. So for persistent storage of data, you have two primary options available in AWS. The first is Amazon S3, that allows you to store data as objects in buckets. And the second is Amazon EFS, which is an elastic file system. Both have different features and benefits for you as a developer, so I'll discuss each of these in detail. First, let's take a quick look at Amazon S3 and object storage. So S3 is an object store. And object storage is different to file storage. It takes each piece of data and designates it as an object. Data is kept in separate stores known as buckets instead of files and folders. The data is bundled with associated metadata and a unique identifier. So by contrast, file storage systems store data as a single entity in a folder to help organize it amongst other data. This is often called hierarchical storage. It imitates the way that paper files are stored. And when you need access to that file, the operating system needs to know a path to find that file. S3 scales elastically. It contains petabytes of customer data for millions of customers, and the storage grows automatically to meet your needs. It's also highly durable, offering 11 nines of durability. So if you store 10,000 objects in S3, on average, you might lose one every 10 million years or so. It supports versioning, so you can save multiple versions of an object, and that can be useful if you need to preserve, retrieve, or restore data based upon versions for the object. It also lets you recover from any unintended user actions, such as deletions or application failures. S3 provides lifecycle management options which let you expire objects at a given point in time or automatically move storage classes when a set amount of time has passed. So those sorts of features help you manage data freshness and cost. Storage classes also let you choose the data access level to balance your workload's needs with your costs. So you can archive data in S3 Glacier, for example, at very low cost. Finally, S3 natively integrates with Lambda as an event source. So this means that events in S3, such as a put or a delete, can also then trigger a Lambda function. And this is incredibly useful for building data processing pipelines or workloads where the arrival of data drives some sort of workflow. So the integration event with Lambda means that the event in S3 triggers a Lambda function automatically. Here's an example of a simple language translation workload that I built, and you can see the example at this URL on the screen. When the source text is stored in the first S3 bucket, this triggers the batching Lambda function, and that function then stores its output in a translation bucket. And when that object is written to the second bucket, that invokes the translation Lambda function, and that calls Amazon Translate and stores the result. So if very large numbers of objects are written to this S3 bucket, Lambda scales up the process for handling all the extra load. So this is a really useful pattern when you're building scalable applications. I've published quite a few different examples of how you can do this, but this is one of the key ones I use to show just the basics of how it works. So setting up S3 as an event source can be done from the console fairly easily, but also from the CLI as well. And if you use the serverless application model, also known as SAM, you can do this directly in a SAM template as shown here. So SAM is a great way to define serverless applications using YAML, and that can help you build applications more quickly. This example shows a Lambda function defined in SAM. So at the top, you'll see it specifies the runtime, Node.js, the memory size, the location of the function, and the IAM policy for the function. And then in the events section further down, this configures the S3 event source. So here, this sets the event when new objects arrive in the input S3 bucket, and it uses a filter to restrict the event to only objects with a suffix of JSON. So once this SAM template is deployed, it will then create the Lambda function together with the associated event source mapping. Now, once a Lambda function is invoked by S3, the function is called with a JSON payload with details about the S3 event. The payload looks like this. It shows you the bucket name, the object key, and other important details about the event. The important thing to note here is that S3 doesn't send the object data itself, but really just a reference to the object. Once you have the event payload shown on the left here, you can then use the AWS SDK in the Lambda function to interact with S3 from your code. On the right, I show you how you can do this in Node.js, but you can make use of your preferred runtime instead. The SDK provides methods that make it very easy to read and write to objects in S3. So in this first section, you can read data from S3 in the Lambda function in a one-line call to the AWS SDK by using the getObject method of the AWS S3 class. You pass in the bucket name and the key as parameters, and it will return the object. Similarly, when you want to write objects back to S3, you use the putObject method. In this case, you also provide the body content and the content type. And when this returns, the object is then durably stored in S3. So when should you use S3 for Lambda data storage? It's good for use cases where you need the event source integration or you want to store data durably with minimal configuration. If data versioning and lifecycle management are important in your workload, then you can leverage the capabilities of S3 to make this available in your application. When you work with very large files or binary data, S3 is a good choice. And this is especially true if you're uploading data directly from an end user via mobile or web app, for example, since you can upload directly to the S3 service without going through any sort of proxy or API. And that can take the load and the networking traffic away from your application. If you're also using object tagging and metadata capabilities, then an object store like S3 is likely a good way to go for your solution. And also, S3 can be used with AWS Glue for ETL that simplifies preparing data for analytics, or Amazon QuickSight, so you can use S3 as a source for data, making it very fast to produce dashboards and business intelligence reports with no code required. So if you need that sort of functionality, then again, S3 is really a very good choice. You might want to consider alternative data storage options if you need NFS style permissions, or if your function processes large numbers of small files, either by reading or writing, or if you need the ability to append to files. S3 only lets you overwrite entire objects as new versions, so appending data is not available in the service. You also cannot use S3 for mounting storage to map to a file system path, and you can't connect to S3 during the function initialization part of your Lambda function for any reason. S3 provides read after write consistency of puts for new objects in your S3 bucket with one caveat. And the caveat is if you make a head or a get request to a key name before the object is created, and then you create the object shortly after that, subsequently a get might not return the object due to eventual consistency. So if you need strongly consistent operations, there may be better choices for your workload. Lambda also provides local storage options for your functions. So each execution context provides additional storage space in the temp directory. And you can read and write to this space during your function's invocation. This space is a transient cache, which means that any files written here may continue to exist between function invocations, and it has a fixed size of 512 megabytes. Now, typically, this is the fastest I/O of any of the storage options, and it's provided at no additional cost. /temp is always available in Lambda. There's nothing you need to do to turn it on or enable it. And you can access it like any other file system, as shown in this code example. So this illustrates how you would access and extract a zip file to /temp using Python. It's not shared across function environments, so this space is per function context, meaning as your function scales up, each execution environment for a single function has its own 512 megabyte temp space. Contents of /temp are not wiped between warm invocations, so you may see files written from previous invocations in the same function environment. So the best practice here is to use this like you would any other typical temporary storage space in an operating system. Don't depend on contents being there. Use unique identifiers in your naming conventions, and only use it for the needs of a single function invocation. And as with other fixed disk space sizes, if you use it extensively, make sure you clean up after yourself to make sure that if there are any very large files, you don't fill it up and run out of space. So the next option for local storage is Lambda layers. A layer really can be anything. It can be dependencies, training data, config files, really anything you can think of. So the purpose of layers is to let functions easily share code. You upload the layer once, then you can reference it from any function. You can have up to 5 layers per function, and they contribute to the overall package limit of 50 megabytes when zipped and 250 megabytes when unzipped. Layer storage is also part of that general Lambda storage pool per region, where you have a limit of 75 gigabytes. So once you enable a layer for a function, the contents become available as /opt during invocation. Each time you upload a layer, it increments an automatic version counter starting at version 1. Each version is immutable, so updating a layer's contents always creates a new version. To have a function use the updated layer, you simply change the version of the layer in the configuration. So by default, your layers are private, but there is some built-in support for sharing securely to other accounts. And you can do this using IAM permissions. So you can share a layer with other AWS accounts or AWS organizations if you're using that, or you can make a layer public for everybody in the world to use. So using layers can help promote separation of responsibilities. It also lets developers iterate faster when you're writing business logic. So layers can help improve the deployment speed because it reduces the size of the total upload during the deployment process. So you can create a Lambda layer in the console or the CLI, and you can also create one using a SAM template as shown here on the right. So SAM has a resource called AWS serverless layer version. You define the layer name, the compatible runtimes, and other attributes here. And then the content URL attribute defines where the layer contents can be found by SAM. So here in this example, it's in the layer subdirectory. Within that directory, you must place the contents in a specific subdirectory that's determined by your runtime. For Node, that's node.js /node_modules. And for Python, it's python/lib/python 3.8/site-packages. So there's a complete list of runtime directories available at the URL on the screen. Then to publish the layer, all you have to do is run the SAM deploy command in your terminal. You can share a Lambda layer from the AWS CLI using the add layer version permission command. And in this example, this shows a command that shares a layer called node sharp, which contains the sharp npm package that's commonly used for image processing. The principal parameter defines who you share the layer with. An asterisk means that you're sharing it publicly. You can also specify an AWS account here if you prefer. Sharing is done per version of the layer, so you have to specify a version number, and anytime you publish a new version of the layer, you have to then explicitly share that version. Lambda always defaults to private visibility for new versions and new layers. It's very important. The statement ID is a human-readable reference. It doesn't affect the policy at all. And there are similar commands available for listing and removing any sharing policies that you've defined. So these all enable you to manage all of the sharing options, but they're only available via the CLI. Configuring a function to use a Lambda layer can be done in the console of the CLI as well, and you can use SAM as well, as I'm showing here. So for a Lambda function to use the node sharp layer that I had in the previous slide, I use the layers property in the function definition. This accepts a list of layers, up to 5 for a single function, using the layers ARN, which also includes the version number, which again is very important. You have to always make sure you import a particular version. So for a complete example of how you could use this, see the repo for the sample application called Happy Path that's listed here. This contains reference templates and code that you can use in your own applications. So when should you use Lambda layers? Layers are useful for sharing code libraries across multiple Lambda functions and sharing libraries with other teams in your organization. If you have a code package that you want to share publicly with other Lambda users, it's also a great solution. You can use a layer to contain a specific version of the AWS SDK. So while the SDK is embedded in the Lambda service, it's upgraded fairly regularly as new services and features are deployed at AWS. So it's best practice to pin the SDK to a specific version in your function, and you can do that using a layer fairly easily. Layers are also the mechanism for using custom runtimes in Lambda. Customers have built layers for C++, Rust, PHP, Haskell, Swift, COBOL, and many more. And that enables developers to use any runtimes that are not natively provided by the Lambda service. So to learn about creating custom runtimes, take a look at the URL currently shown on the screen. Layers may not always be the ideal solution. So if your workload needs NFS style permissions, this is not available by using a layer. And the layer's content is immutable, so it's not possible for the consuming Lambda function to modify its content in any way, nor can you automatically push new content to it dynamically to a Lambda function by using layers. So for this reason, layers are not the best option if you need to access dynamic content or you need to persist new data. Also, if you want to mount storage in Lambda, there are other options available. So next, let's talk about the new feature that we launched a few months back, which is EFS for Lambda. So Amazon EFS is an elastic file system that automatically stores files redundantly across multiple availability zones. So the EFS file system objects have a Unix style mode associated with them, and that defines the permissions for performing actions on an object. On Unix style systems, users and groups are mapped with numeric identifiers, and EFS uses those to represent file ownership. As the name suggests, EFS scales elastically. That means that the space available automatically grows and shrinks depending upon your usage needs. It also offers built-in lifecycle management too, to optimize between SSD performance classes and an infrequent access class. And that can reduce your storage cost by up to 92%. You simply enable the EFS lifecycle management option on your file system when you create the file system. EFS has two performance modes. There's general purpose and max I/O. General purpose is suitable for most Lambda workloads, and that provides lower operational latency and higher performance for individual files. You also choose between two throughput modes with EFS. There's bursting and provisioned. So file-based workloads are typically spiky. They drive high levels of throughput for short periods of time and low levels of throughput for the rest of the time. And so to accommodate this, EFS is designed to burst to high throughput levels for a period of time. All file systems, regardless of size, can burst to 100 MB of throughput. And for those over 1 TB in the standard storage class, those can burst to 100 MB per second per TB of data in the storage file system. EFS uses a credit system to determine when file systems can burst. Each file system earns credits over the time at a baseline rate that's determined by the size of the file system that's stored in the standard storage class. A file system uses credits whenever it reads or writes data. For workloads where you need more throughput than bursting allows, EFS offers provisioned throughput. In this case, you explicitly choose the throughput. This is for workloads with high throughput to storage ratios, in other words, where you have fewer files, but a lot more file access activity. There are additional costs for using provisioned throughput, though, so just be aware of that. For most Lambda-based workloads, we recommend that you use the bursting throughput mode. In either case, the total throughput is divided across the number of concurrent Lambda functions. To configure EFS for Lambda, first you create a new file system, and you can do this from the EFS console. It takes you through a series of steps, and there you specify the backup and the lifecycle policy, performance mode, and throughput mode, together with any encryption preferences. Finally, this is where you create an access point to the file system. So an access point is an application-specific view into an EFS file system, and it applies an operating system user and group and a file system path. And so any request that's made through the access point will go through to that file system. The file system path is exposed as the access point's root directory. So applications that are using the access point can only access data in that directory and below. You can optionally also configure a POSIX identity and a root directory for all connections to the access point. And if you specify the owner for a root directory, EFS will automatically create it with the ownership and the permissions that you specify once a client connects to the access point. You can also define an access point in a CloudFormation template by using the AFS EFS access point resource. The same POSIX configuration parameters from the AWS console are also definable as CloudFormation attributes. When you deploy a stack containing an access point resource, the operation requires the Elastic file system create access point action permission. Now, once you've created the EFS file system and the access point, you can then connect it to Lambda via the console. There's a new file system panel that you might already have seen to show you how you can connect to an access point and specify a local mount path. The mount path directory is where your Lambda function will be able to access the file system during invocation. So in this case, it's /mount/test. Alternatively, you can also perform the same console actions in a SAM template. So using SAM, you can add the EFS configuration to a function using the file system's configs property. And as before, this function then has access to the file system at the local mount path directory. So there are a few important things to know about how EFS works with Lambda. First, the Lambda function must have the same VPC configuration, and this includes which subnets are selected. So the subnets chosen for your EFS configuration should also be the same as for your Lambda function. The process of attaching an EFS access point happens when the Lambda service first starts a new execution environment for the function. The EFS mounting process occurs in parallel with other tasks that are going on, so it doesn't impact the overall cold start latency of a function. In the warm start process, where the execution environment is already being used again in the subsequent invocation, the EFS mount is already persisted and reused, so it doesn't add any additional latency there either. The mount path is available during the init part of the invocation. So this is the part of the code that runs outside of your handler. And it means you can read and write to the file system during function initialization, which remember, you couldn't do that with S3. And that allows you to reference and initialize libraries and packages in your runtime before the handler starts. You can configure the mount path per Lambda function, and you can choose which path you prefer. And the file system is available to all concurrent function environments. So as your function scales up, each instance can access the mount path. This makes it easy to share data and state between different concurrent environments. So the total throughput for your EFS file system, whether it's configured for bursting or provisioned mode, is shared across all concurrent Lambda execution environments. This means that as your Lambda functions scale up, you have to divide the total throughput across the total number of environments. A single EFS file system can support up to 25,000 concurrent connections. This is any combination of connections from instance-based compute like EC2 or Cloud9, and also on-demand compute like Lambda. Also, you can use EFS with provision concurrency. So for workloads where you need to reduce the cold starts to double-digit milliseconds, but you also need access to a dynamic elastic file system, the combination of these two features can be a really good solution. So what I want to do is just take a few minutes to show you an example of how you could use EFS with Lambda. So I'll just exit out of here. Pull the screen over here. Okay, so here is my AWS account. And the first thing to see is if you go onto services and go to EFS in the dropdown, you'll see these options. Now, I already created this one earlier for the demo, but if you wanted to create a new file system, I just click Create File System there, provide a name. I also have to provide networking configurations, so select a VPC for it to belong in. And that will just create a new file system. So it's pretty straightforward, and you don't need to specify a size or anything because it's elastic. Now, what I did a few weeks ago is I created a series of examples to show how this works in this GitHub repo in AWS samples. So I've got 4 or 5 different examples here to show you how you can then use an EFS mount within your Lambda functions. So to show you how this works, I've created a Cloud9 instance. So that's basically a virtual IDE that runs within AWS. And what I can do in Cloud9, because Cloud9 under the covers is really running on an EC2 instance, I can mount the file system by using a standard Linux mount command. So I'm just looking through my history here. That command I ran earlier mounts the file system that you saw previously in this section here in EFS demo. So when you create the system, you make a note of the file system ID to do this. Now, once that's been mounted to EFS, I've CD'd into that directory, and you can see I've put a file here called video.mp4. So this is a file that exists on the EFS mount, not within Cloud9 instance itself. And then I cloned this GitHub repo down to my Cloud9 instance so I can show you one of the examples. So in this example, what we're going to do is have a Lambda function that accesses this MP4 file, and it's going to take a screen capture for every second of video and store that within the EFS mount. So the way that works, let's take a look at the SAM template first. I'll just move this up here. I'll just make that a bit smaller. So the key thing to do here, if you've not seen a SAM template before, this is where we can specify the Lambda function and also its network configuration, the events that cause it to run, the access to the EFS mount in file system configs, and then a bit further down, this is the IAM statement that provides access to all the resources that this particular function needs. And then just at the top, I've set this up so we provide parameters saying what the path of the video MP4 file will be, what the mount path of the directory is, and various security groups, subnets, and so forth. So to save time, I already SAM deployed this example. If I go to Lambda, this is the function that was deployed just here. Now what I'm going to do is I'm going to start this running because it takes a couple of minutes, and then while it's running, I'll go back and talk about the code that's currently running. So I'll just kick this off. Now back in Cloud9, let's take a quick look at the code itself. I'll open up this process file app.js. So what this is doing is there's a library called ffmpeg that will do all the hard work of separating the frame grabs out of the video. So I created ffmpeg as a Lambda layer. You might have seen it in the template just over here. I was importing this layer just here. So this is a public layer that I created. And over in app.js, where it's actually only a one-line handler, what it's going to do is run a command line command here to invoke ffmpeg, load the file from the EFS path, and then create a series of screen grabs based upon 1 frame per second and the logic that's based there. So that's all it's doing. There's nothing particularly complicated in terms of the code that's running. But this video file is about 70 or 80 megabytes, so it's a fairly large video. But now this has been running for a minute or two. What you'll see, if I just do this, you'll start to see there are other files that have appeared in addition to the video. And as I ls, this will start to grow each time I do this because it's continuing to produce different files. Now, if I open this directory, I can open up any one of these. You'll see it's actually just a screen grab from a video. So the Lambda function right now is outputting these files into the EFS environment. And if I go back to Lambda, it should say it's finished by now. So that whole thing took 145 seconds to, actually took 68 seconds to complete. So what you can do with this sort of Lambda function when it's mounted to EFS is you can run longer jobs on larger files and then process the work and put the result back in the EFS directory. It also means if you're doing very, very long tasks that take longer than 15 minutes, then instead of running out of time your Lambda function, you simply save how far you got up to and let the next invocation of the Lambda function pick up the work and continue. So to look at this example further, just go to this GitHub repo, and I can paste that in the chat afterwards, where you can clone these examples and run them and see how it works. What I'll do now is I'll just show you the last couple of slides I wanted to cover. So the key question is, when should you use EFS over S3 and the other options? So if you use very, very large libraries, and they're typically larger that will fit into a Lambda layer, for example, then you can store these in EFS and import the modules that you need from there. So alternatively, what you can do, if you have dynamic libraries with content that changes and you want to ensure that the Lambda function is always up to date with the latest version of the code, EFS is also a good choice. So Lambda layers are static, but EFS allows for dynamic imports. We also have many customers who are running machine learning models as well, and they use EFS. So often they use EC2-based processes, which save the models to EFS, and then they create Lambda functions for machine learning inference, which loads the models from the file system. Also, when working with a very large number of small files, so EFS can be cheaper and more performant than S3. And this is because S3 charges for gets and puts, whereas EFS billing is based upon throughput and data storage. And since you can specify the EFS throughput, you can create Lambda-based workloads with very fast I/O if needed. So where you need file system operations as well, like appending to log files, EFS can also be a good choice. S3 is object-based storage, and it doesn't support file operations such as append. So for workloads that manipulate file contents frequently, it's usually better to use a file system like EFS. Also, if you need NFS permissions, which aren't available in other solutions, and for workloads where you need to share state across concurrent Lambda function environments, EFS lets you do this. So when should you consider alternatives to EFS? Well, really, if you need an event source binding in Lambda, you cannot invoke a Lambda function from an EFS file event in the same way as you can for an S3 object event. So while data transfer is included when the Lambda function and the EFS mount operate in the same availability zone, if you use cross-account VPCs, there can be additional data transfer costs. Also, there's no cross-region or cross-AZ connectivity at this point. So here's just a quick table that summarizes all of the key differences to think about. I'll just call out a couple of important ones here. So first, layers and /temp have maximum sizes, whereas EFS and S3 do not, they're elastic. And both /temp and EFS are file systems, but S3 is an object-based store, so that's a really important difference. S3 is also the only storage type that lets you natively integrate events with Lambda, and that's really important if you need to build serverless applications. In terms of file operations, those are supported in /temp and EFS, but not S3. The pricing models vary by service, so S3 costs are based on storage, number of requests, and data transfer, whereas EFS does not charge by request, but there is a throughput cost in the provision mode. S3 offers integration with services like Glue, so if you need that for processing for analytics, and also QuickSight, so that can make it very easy to create business intelligence dashboards directly from data in S3 buckets. And finally, it's worth comparing the relative speed of data access from these different systems. So /temp and layers are the fastest, since they exist in the execution environment where the code is running. S3 is generally fast across average to large object types, both for reading and writing data. And EFS can be very fast, so especially for large numbers of small files or where you're using provisioned throughput. And you can also use a combination of these solutions in your workloads. So here's a quick example. So if you imagine a streaming service like Netflix, where they host full-length videos, but there's some sort of UI where there's a fast forward feature, and that shows you individual frames of a video matching where the viewer is fast forwarding to. You may need to create a system where you can create GIF animations that provide a preview of the next few seconds. So to do that, you would want a Lambda function that generates all of those frames and all those GIF animations. So in this case, the original MP4 file is stored in the EFS mount, and this is the full-length movie. So this Lambda function would then mount to the EFS file system via an access point and read this MP4 file. So then, to do the graphics processing, you need a fast graphics library like Sharp. And so here we'd package the Sharp layer as a Lambda layer. That could be used by the Lambda function. The Lambda function then could extract 1 frame per second of video. And to generate the GIF previews, let's say it stores the last 10 frames in the /temp directory storage. And then once there are 10 frames, it can then create the GIF animation. And finally, it could then store the individual JPEG frames back to the EFS mount for further processing. And it could take the GIF animations and save those to an S3 bucket for the front-end UI to access. And then you would delete the local frames out of /temp each time a GIF is generated. So in this approach, the static code library is stored in the Lambda layer. The intermediate data that's needed to process GIF animations is saved in /temp. And then the publicly distributed GIFs we put in S3. And then for processing thousands of individual frames of video, those are saved in the EFS mount. So I've covered a few things very briefly today in the multiple storage options you have available when you use AWS Lambda. S3 offers object storage with lifecycle management options that you can use in your workloads to expire and archive content or to move data to lower cost storage. It also has powerful event integration into Lambda, making it simpler to run compute operations in response to S3 events. EFS for Lambda is a fairly new feature that can be helpful for a variety of different use cases. So for workloads with libraries that are too large for a Lambda layer, or machine learning models for ML inference, EFS can be a really good choice here. If you need to share files across concurrent Lambda functions, or an EFS file system that can mount across function environments, that can make it very easy to pass data between invocations. It's also a good option for applications that are processing large numbers of small files, as I was showing in the demo. So these data storage options are not really an either-or choice. You can use them in combination to solve specific challenges, and that can let you create some really powerful solutions easily with Lambda. So thanks for joining me for the brief overview of these different storage solutions. I'm really excited to see what you build. So my name is James Bezic. This is my Twitter handle and email address. That's the most important part here. And don't forget to check out Serverless Land. We put a lot of DA content there on blogs, code samples, videos, and other things that can help keep you up to date. But I'm happy to take any of your questions now as well. Thanks, Jack. You're welcome.
And for anyone who's unfamiliar with the interface, the mute button, if you're in the app, is going to be almost directly in the top center of the screen if you want to unmute yourself to ask, or feel free to type in the chat box. Well, you covered everything, James. It's amazing.
Success.
Actually, I had a quick question. I'm sorry, I was looking for the mute button. So with the EFS on Lambda, is there any, I guess, throttling or concerns with, I guess, invoking too many functions and mounting EFS, or do you have any best practices around that you recommend?
It's really the throughput that you have to control. So if you can scale up to 25,000 connections. So most workloads can fit with that fairly comfortably. But if you're going to be scaling up pretty aggressively and you're going to be using a lot of throughput, then I'd recommend looking at the provision throughput option. But what we're seeing people use this for most of the time is they tend to be fitting within the default options. So whether they're loading large machine learning models or lots of small files, generally they're using it in the similar sort of way that EC2 users were using EFS as well.
Okay. And yeah, I guess, yeah, so I guess you would, be constrained by the same limits you would with EC2. So, okay.
Yeah,
that makes sense.
I think one of the things to watch with this is that it opens up the possibility that you've got the ability to write to multiple files simultaneously from lots of different places. So you can get fairly inventive around what you can do here. But obviously, if you have the same scaling Lambda function publishing back to the same files and the same EFS mount, you can overwrite your own data. So there are some file management issues you want to be aware of, so you don't do that. There's a question, can the EFS volume be shared with EC2 and other services? Yes, it can. So in the Cloud9 instance I was showing in the demo, Cloud9 is really running on EC2. So you can mount an EFS volume on EC2 like any other type of Linux file system. So that's actually one of the really useful workflows we see from lots of customers where they're using EC2 to build models or to create code packages, and they're publishing them to EFS from there, and then Lambda functions are then picking up that data via EFS. Thank you, Gabriel. Much appreciated. One of the things I will add, actually, So when you're looking at building these solutions, probably the most complicated piece is the networking part, because EFS is a solution that runs inside of VPC. So if you're not used to doing that, it gets you back in the realm of subnets and security groups and this sort of thing. So the GitHub repo I published, I have some good templates there that will handle most of the heavy lifting and configure the Lambda functions to automatically work within a certain VPC. So that, to me, when I was picking up using this and first started using the feature, I found that it was the hardest thing, because I've been using serverless for so long, I've kind of forgotten how networking works. So when you use these sorts of services, there's something to be aware of. Yes, I did copy it to the clipboard. I wonder if it's still there. It is. Great. Yeah, that's the GitHub repo. So if you think of any other questions at all, feel free to send me an email or DM me on Twitter with anything. I'm happy to try and help. Also, we have reInvent coming up very soon, just after Thanksgiving. This week is running for 3 weeks, and it's all on demand, all virtual, and all free. So definitely tune in and see some of the feature launches we'll be putting out there, in addition to serverless land, the other side I was showing you. Oh, second question. Is the throughput of EFS managed through CloudWatch metrics? Yes. So EFS does publish metrics through the CloudWatch, so you can set alarms on those metrics. Fortunately, EFS has been around for quite a long time, so the integration throughout all of the different monitoring and observability systems is pretty good. How long before the link to this presentation is available? I definitely want to revisit this presentation. I don't know, Hugo.
I could answer that. Yeah, we'll get that video uploaded and posted to the meetup site tomorrow.
Great.
Great. Well, James, thank you so much for the presentation tonight. We really do appreciate you joining us, and thanks to everyone as well for joining our meetup, especially Tuesday night. Again, anyone who has any interest in presenting in future meetups, any content they'd like to see, please definitely engage with us through our meetup pages or through our Slack team. Other than that, thanks again, and enjoy your nights. Thanks, James.
Great. Thank you so much for inviting me. Talk to you all soon.